Thanks for your introduction, and I would like also thank the organizing committee for organizing this year's conference. My name is Chenghong, and I'm currently a PhD student from the Hong Kong University of Science and Technology, Guangzhou. And in this talk, I will mainly talk about the shuttle and swap co-optimization in quantum charge coupled devices. So this work is collaborated with Xian and Jingbo Wang from the Beijing Academy of Quantum Information Sciences, and also our PhD thesis supervisor, Xian. So before I start, I would like to give a bit background on this topic. So currently we are in the ISCA area that there are many experiments have been done to show the quantum advantages. So for example, the random circuit sampling, learning from experiments, and certified randomness. Although there's many significant progress in demonstrating the power of quantum computing, but there's not yet not yet for the practical applications. And also, John Prisco have pointed out the quantum devices are going to be larger and towards the fault-tolerant applications scale. So it means we will have more qubits and higher accuracy. So for the first talk, Yuchen talked about the superconducting devices, and from previous talk, the speaker talked about the neutral ion device. So in this one, I will mainly talk about the trapped ion devices. So why trapped ion? So the trapped ion have many advantages. For example, there's long coherence time. It has been demonstrated by Tsinghua University. The coherence time can reach up to 5,500 seconds, and also it has the highest fidelity of quantum gates, and the state preparation and readout are more direct, and the connection has been shown it is all-to-all, and it ensures a large quantum volume. Also, physical swap is spotted, and also trapped ion quantum computers do not need extreme ultra low temperatures, so the cost is much lower. So the most fundamental device is known as the trapped ion linear tape devices, and it has easier calibration and simplified optics, as well as reduced hardware costs. So in such device, the entire chain shifts back and forth to operate all qubits, and with gates applied only to those qubits that in the execution zone. So to be concrete, so if we want to apply any 2 qubits, we can only do so in this yellow area, which is in the LM or LD zone. And if we want to apply any qubits outside this area, we need to have some movements, and this is known as shuttle, which could cause a lot of fidelity loss during this process. And also, for such TILT devices, there's many problems. According to IonQ's report in 2018, for such device, we can only contain up to 180 qubits inside of this device. And also, even though we can have 100 qubits in such device, the inter-ion spacing reduces, making it difficult to selectively pulse a qubit using the laser controllers. And also, the 2-qubit gate implementation is challenging. So, to be simple, purely rely on this device is not good, and since it has limited scalability. Then following continuous proposal, they have investigated the QCCD, which is known as the quantum charge coupled devices. And basically, for such devices, it consists of several traps, and the traps that can interconnected with shuttle passes. So for this graph, this is a single trap, and they are interconnected with these shuttle passes. So within this single trap, all these qubits are all-to-all connected. So we can do any operations within this trap. So the other problem comes with this kind of devices that the physical constraints can limit the 2-qubit gate implementations. For example, if we want to implement 2-qubit gates between this trap and this trap, we need to perform the split and move and merge operations to move these red ions or qubits into another trap to make the 2-qubit gate implementation here. And this is quite analog to the TILT devices that the whole process we refer as to shuttle. So this shuttle also have costs like to slow down the circuit execution time, but also like decrease the circuit fidelity. And analogs to the quantum computer, classical computer architecture, we also need to develop a quantum computer architecture. And so for those of you who have known about the superconducting devices, the typical process goes like, if you have received the circuit, then you, based on the topology graph, and you insert some swap gates, then you perform the operations. And so for the QCCD device, there's quite limited literature on this topic. For example, Wu and Wu in HPCA 2021 and HPCA 2025 have proposed the compiler design for the single trap device, which cannot directly apply to QCCD. And also, previous work by Murali and Saki, they are only focused on the limited QCD topology. So they have not attempted to empower the compiler's ability in reducing the shuttle operations. And also there have been also proposed some SAT methods that it may have limited scalability to these cases. So in order to solve these problems, we propose async, which mainly to provide a software framework to run quantum applications on QCCD device. So for this, we want to decide which irons to use and schedule the iron movements, and we also want to use the scalable compilation, and we hope we can achieve low shuttle number and higher success rate. And also we hope to give some insight and guidance for the future QCCD. And so to be simple, in this program, we receive the QCCD topology and some quantum applications or quantum circuits. Then it's based on pre-processing and initial mapping and searching framework. Then it's then processed to the simulator to have an estimate on the success rate. So currently there are many challenges. For example, the previous work formulated this kind of problem are only focused on the ions that are already in the trap. So it makes the problem that the topology graph will dynamically changes. So if we use some compilers, then we need to reuse this topology graph. And also, it means that the compilers for superconducting devices cannot directly be applied. And also, we can notice here, if we want to shuttle an ion from one trap to another, we always accompany with swap operations, which can also cause a lot of cost to this case. So in order to solve this, we mainly use well-known techniques. That is we formulate the QCD topology as a weighted graph. So for this topology, we convert into this graph, and each read ions basically means the ions are already loaded in the trap, and the white circles means that it has still some rooms for incoming ions. And these edges connected are represented. They have operations that can be done to either swap the ions or shuttle the ions from one to another trap. So, and also these dashed lines and solid lines represent the cost what occur when applying these operations. We typically select that the shuttle operations have higher cost than the swap operations. And here are some rules that for us to determine what operations we are applied. So once we formulate the QCD topology into this graph, we can directly use the superconducting devices. And so we only care about the swap operations. Every time we apply swap operations, we need to check what kind of conditions have been applied. Then we convert back to the QCD operations. And then we can have the shuttling schedule operations. So this is also quite simple. Basically, if we give an example, we want to apply Q0, Q1 in this graph, and we basically choose the shortest path to another one, and also look at the operations, and we select the score with the higher one. And we can continue to do this until the end. Then after we have these algorithms, we need to evaluate the programs. For evaluate the program success probability, we select the 1-qubit error, 2-qubit error, and ion trap transport error and decoherence due to the longer execution time. So for the single qubit error, since quantum information stored in the iron's internal states remain unchanged during spatial movement, so we fix the 1-qubit error, 1-qubit gate. The fidelity of 1-qubit gate is 99.69, and also the ion shuttling method have could lead the trap increasing the heat, so this would lead to the gate fidelity decreases. So we have this formula to characterize that. And also, since the shuttle have 10 cores, we model it as this. And there are several gate implementation time differs from the different gate implementation methods. So I will talk about later for this. And the program's success rate is computed as the product of individual gate fidelities. And we test 6 applications, and we test different topologies and trap capacities and different gate implementations. And we use metrics such as shuttle number, shuttle swap number, execution time, and success rate to rank the performance of our compiler. And so we mainly compare our compiler with these 2 compilers, and we can show that for the shuttle number, we can achieve an average of 25% improvement, and it can achieve up to 90.2 max improvement. And also for the swap number, it can achieve up to 6.6 max improvement, and also 1.7 average improvement. And these improvements are basically from our weighted graph formulation. Since we really use this swap and the shuttle cost in our formulation, we want to minimize both the costs that occurs in these operations. And because we reduce the shuttle and the swap numbers, the success rate will also increases. And we also conduct some optimality tests. Basically, we use some ideal cases and perfect shuttle and perfect swap. It means perfect shuttle means the shuttle will not introduce heat to the trap, and perfect swap, it means it will not also count for the gate implementation time for this. So these are basically the upper bound for the exact solutions. And we can show that the number of our compiler can actually achieve near optimal performance to many applications, but you may notice that QFT, we can achieve good results in perfect swap, but for the perfect shuttle, there's still a huge gap here. So it means that we still have room for improvement to improve the shuttle operations. And also, we mentioned that we choose the weight of swap and shuttle cost to guide the scheduling, and we also conduct the sensitivity analysis to these hyperparameters, and we can show this performance that remains almost consistent. And we also test the scalability analysis, and we show that our compiler is better for large application size, but with a small chip capacity. And then we conduct some architecture insights to select what kind of topologies that our compiler is best to execute on, and also what kind of chip capacity that our compiler is good at handling that. So this graph is a bit messy, so let me summarize that. So for this kind of QCD topologies, that grid and circle topology is better, and also chip capacity with 10 to 15 is better to achieve the higher success rate. And this grid and circle topology is better is actually follow the developed roadmap to the continuum, and And they are actually building such kind of devices within their roadmap. And also, since the gate implementation can have different parameters to be tuned, so there's 4 gate implementation types. So there's going to be some different execution time on this point. So we also test the success rate of different gate implementations. So for near-term applications, we would like to prefer the PM and FM gates. And for applications with long-range gates, we would like to prefer FM and PM gates. So for the future work, currently our work are only focused on the purely gate ion scheduling tasks, and to scale up the quantum computers, we need to consider the QAC protocols. So for future work, it may be good to consider the QAC protocols on how to schedule on these QAC devices. And also, we also noticed that there is another kind of devices that connect with optical fibers. So it may also be interesting to investigate such kind of devices. So to conclude, so we provide a software stack for QAC device, and we can both reduce the shuttle number and swap numbers. And we show that our compiler is near optimal in swap number, but still have some room for shuttle operations. And we also provide some guidance on hardware configurations. And with that, thanks for your listening.